Hi, I'm Alex Lamb, author of the Roboteer science fiction novels, and you are watching Secrets of the Universe, the thrilling, inconceivable video series in which I answer every single thing that there is. Anyway, what are we going to cover today? Well, I got 2 video requests in my YouTube channel. This is number 2. I'm very happy about it. This one is black holes. I did a previous black holes movie. I didn't like it very much. I've come back and tried again. So anyway, the black holes. What is a black hole? We all know what a black hole is, ladies and gentlemen. A black hole is the exciting nugget of sucky-inny stuff that lives in space. That somehow lives after stars have gone pop, which pulls things in and is very scary. Ooh, yes, there's that. But more technically speaking, in greater detail, what is a black hole? Well, there's a thing called a Type 2 supernova. What is a Type 2 supernova? Type 2 supernova is an event where you start off with a large blue star that burns through all its fuel super fast and becomes a big red puffy star. And then what happens is that it runs out of fuel. It burns through all its fuel terribly fast, and so it goes from this very inflated, self-indulgent state, rather like certain politicians that one could mention. It runs out of its fuel, and then at that point, it cannot sustain itself. So all of the mass of the star, which is still stuck in the gravity well, squeezes in together. It's sort of sucked in because the radiation pressure isn't holding it out. It squenches down into a tiny spleen in the middle. And what this does is it causes a bounce, a terrifying explosion-y bounce, where the stuff goes in and pops back out again. And that pop is called is what we think of as a supernova. Terrifyingly large, super bright explosion that basically incinerates everything pretty much within about 3 light-year radius, which is quite large. And what it leaves behind it after this enormous pop is the stuff that was squeezed all together in the middle, some kind of dark, hot, spinny remnant, which is left over from this explosion. And sometimes this is what's called a neutron star, another sort of hypothetical astronomical thing that's very hard for us to look at, but we think we see. A neutron star, which is basically a condensed ball of kind of neutron-y stuff that then sits there and spins around terribly fast. And we're pretty confident that that can happen, ladies and gentlemen, because some of them still have bright spots on them that then send out sort of like little sort of bright beams. So if you're standing in the right direction, you can basically see these things that look like very bright periodic pulses, but then sort of it is kind of like a lighthouse, but it's a kind of an accidental lighthouse in space. And when people first saw these things, they thought that that was aliens. Wasn't. It was a dead star. Anyway, that's not black holes. A black hole is what happens when the star is that much larger, or the explosion, the compression is that much more intense, and it passes a specific critical threshold, beyond which the compression of the matter is so much that basically not even light can escape. And then you don't get a degenerate blob of matter. Then you get a sort of, if you like, a degenerate form of space. You get basically a sort of a very odd object that's sort of defined pretty much just by its sucky-inny characteristics and seemingly very little else. And then that sits there being very hard to think about or understand. So we don't really know exactly what happens under those conditions because it's very hard to look at a black hole, very hard to observe one, very hard to visit. Anyway, but why is this a big deal? We think this is going on. There's plenty of great evidence out there in space. For instance, rotational curves of galaxies suggest that there must be something with a sort of similar density and properties to a black hole sitting in the center of every galaxy, like an anchor holding it in place. So all our nice sort of, like the sort of wheelie, spinny bit that we're in gets to continue on its nice arcing path because there's this crazy hell nugget right there in the center, acting as a sort of a gravitational hub. And we see other such places at smaller scales, other places where stars have collapsed, where there's the implication that if it's not a black hole per se, there's certainly something tremendously like it. Anyway, you get the general idea. Why is it a big deal? Why do people in science think, or tend to think about black holes a lot? Well, because, ladies and gents, it's one of those strange and exciting places where relativity, the science of large things, and quantum mechanics, the science of little fuzzy things, get to actually sort of come together. Because in the black hole, what you have is a lot of very heavy stuff, and it's all squeezed together terribly close. Perfect conditions for quantum gravity research, if only we could go there. And this is the thing about quantum gravity, which is why it's crunchy, is that we have had two major scientific fields in particle physics, those two topics, trying to work with them for over 100 years. Relativity and quantum mechanics, you try putting them in the same room and they fight. They fight like unhappy cats. They just don't want to get along. They just don't want it, ladies and gents. And so that's very problematic, because the physicists are like, please look, here's a goddamn bowl of milk. Will you just simply do a thing? And they're like, no, so that's relativity and quantum mechanics. And therein lies the rub. People have been trying for ages to solve this particular problem. Black holes, and thinking about black holes is a great way to study it. So what's the work that's been done around this? Well, there's been several interesting things done in black holes, although they're still, frankly, terribly mysterious. One of them, the basic, if you like, the traditional idea, is that you have what's called an event horizon. The event horizon is the sort of the distance towards a black hole beyond which not even light can escape, and once you go past that, you're screwed. So that's outside edge, and then in the center, right there in the center, is the singularity, as it's called, which is the point at which all of our understanding of physics breaks down. None of the equations make sense anymore. There's all these infinities popping all over the place. It's rubbish. So people have thought for a while there's probably something wrong with that traditional model. Singularities are kind of, it's sort of like saying, oh, and then there's some magic stuff happened. So anyway, that's the traditional idea, but it is legitimately a point at which our understanding of physics breaks down. There's been some really interesting and exciting work done since. You'll be unsurprised to hear that it's mostly about the edge of the black hole rather than what happens on the inside. So for instance, Stephen Hawking, everybody knows him, discovered Hawking radiation. And what Hawking radiation is this hypothetical form of radiation that happens at the edge of black holes, where little tiny particle pairs that spontaneously, theoretically at least, form in normal space-time all the time near the edge of a black hole. What happens is they get formed in pairs, and instead of going and squidge back together, what happens is that one of them ends up falling into the black hole, and the other one is like, I'm free! And so what this means is that there's a net ejection of particles from the surface of the black hole, and consequently, weirdly, despite the fact they're swallowing particles, the black hole shrinks. Crazy times. People think that's probably true. Then other exciting work that has been done since. Also, there's a bloke whose name is Juan Maldacena, if I have correctly pronounced his name. I have no idea if I have in fact done that. But anyway, he's a tremendously clever individual, and what he figured out a relationship to do with information and black holes. He figured out that the information content of a black hole, and that's how much stuff there is in it, if you like, or how much stuff it represents, seems to be defined by the surface area of the black hole. It's almost as if all of the stuff related to a black hole is trapped on the boundary, and it's not related to anything else on the inside. So that's weird, but that has spawned this whole area of the holographic principle, as it's called, and all the exciting subsequent research that's done where now, you get to sort of sit round and smoke pipes in physics departments and talk about anti-de Sitter space and so on and so forth. That all happened because of Maldaceno's exciting holographic thing. Anyway, so some tremendously exciting, wonderful work that's been done. What do I think is going on? Because you don't come here for the simple, like, what actually is the science. You come here for the crazy, ladies and gentlemen. What do I think is going on? Well, I've tried to model black holes multiple different ways. You'll be unsurprised to learn. I've got one favourite one, and that is where you model space-time as what you might think of as an irregular mesh. You essentially divide space-time into a bunch of tiny little nuggets. These nuggets, you've joined them together with little associations. So you end up with space that's sort of looking like a madman's fishing net that's all made of like triangles and trapezoids and irregular little connections. It doesn't look regular. Anyway, that's space. And the mad thing about this network is that it's constantly growing and shrinking. So little nuggets sit next to each other. Sometimes they get glommed together and become one nugget. Sometimes what happens is nuggets split in two, and you get little new patches of space-time being formed. And you can do quite wonderful, exciting things with a description of space-time like this. But what's really exciting when you use this approach to model black holes is that you get this effect where the force that's making the nuggets collapse together essentially makes a truly degenerate place where the fishing net looks really shit. You end up getting this effect where you have the boundary of your black hole, if you like, your event horizon, and then what's inside it? Basically nothing. The amount of space that's inside the black hole is near zero because that's a place where the spatial nodes are all shrinking down onto points. So really, the black hole in that case is defined by its boundary. It looks pretty much like Maldaceno's sort of holographic principle kind of model. It's like, in that case, your black hole, if you like, is like a bubble of nothing. All of the magic really does happen at the edge. And that's why I like that particular version terribly much, because it's sort of like, anyway, you get the idea. Black holes, ladies and gentlemen, that's probably enough for today. I think I've witted for a full 15 minutes. Thank you very much for watching and listening. Tune in next time for more outrageous nonsense and some science to boot. Hooray!